Hello, today we're going to complete our series on an elementary look at particle physics by looking at what I call designer particles and supersymmetry. We've learnt that quarks, which are fundamental particles, come in three colours: red, green and blue. Of course, they aren't real colours, these are just labels that distinguish a red quark from a green quark from a blue quark. And that is the basis of what's called quantum chromodynamics. There are three colours, and quarks can change their colours. And they change it by rotating. And we use the rotational matrix, the special unitary matrix, SU3, to achieve that. We've also learnt that quarks come in flavours: up and down, charm and strange, top and bottom. So there are three lots of pairs, and they can again rotate between up and down, and mathematically we use the special unitary matrix SU2. And of course, because quarks are fermions, they have a spin, and that spin can either be up or down. We call that plus or minus 1/2. We know that quarks can never be isolated. They are always confined in groups, and I showed you why in the last video. And what we find in nature is that quarks either come in sets of three, quark, 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 or in sets of two, quark and antiquark. And the way it works is that whenever you have three quarks, you always have one of each colour: red, green and blue. The reason, as I explained, was that if you didn't, then if, for example, two of them were red, then they would both have exactly the same energy state or quantum state, and that is forbidden by Pauli's exclusion principle. So there must be something that distinguishes two quarks of the same type. If you had two up quarks, for example, there must be something that distinguishes them, otherwise they couldn't be in the same quantum state, and we call that colour. Or if you have quark antiquark, well then you can either have red anti-red, or blue anti-blue, or green anti-green. The idea is that these combinations, whether they come in threes or twos, are what's called white. That is, red, green and blue together as colours make white, or red and anti-red makes white, blue and anti-blue makes white, green and anti-green makes white, and so on. So the quarks come in these groups. There is some theory now that you could have quarks in larger groups, but those haven't been discovered, so I'm not going to spend much time on them. And now we can, as it were, design our own particles. We know that if you've got three quarks together, we'll start off by looking at the group of three. If you've got three quarks together, we know that each of them will have a different colour. So we don't need to worry too much about that. But let's instead consider what combination of flavours and spin you might have in a quark combination. A combination of three quarks is called a baryon. A combination of two quarks is called a meson. And baryons and mesons together form hadrons or hadrons, and hadrons are fermions. We'll see this a little more clearly in just a moment. Just at the moment, I want to design some particles. So let's start with a particle that we know very well. We'll start with the up, spin up, spin up, down, spin down. Up, up, down, that is recognisably a proton. It has a charge of 1, because an up quark has a plus 2/3 charge and a down quark has a minus 1/3 charge. So it's 2/3 plus 2/3 minus 1/3 gives you a charge of plus 1. And what is its total spin? Well, it's plus a half, minus a half gives you a spin of 1/2. That's a proton. But suppose I took a particle and made it like this: up with a spin up with a spin up, down with a spin up. Remember, down doesn't tell you what the spin is. Down is just a name of a particle. A down quark can spin up or down. If I did this, I don't know what it is, but I can tell you that its total charge is still going to be +1, because it's 2/3 plus 2/3 minus 1/3. But its total spin is now a half plus a half plus a half is 3/2. And a particle with a 3/2 spin is not a proton. In fact, we call it a delta plus. Now, you won't find a delta plus very self-evidently out in nature because it decays very, very quickly. In fact, all the particles that I shall design decay very fast into protons and neutrons. Even a neutron decays into a proton when it's a free neutron, as I showed in the last video, in about 15 to 20 minutes. All the other particles decay in less than a second. So let's design another one. What happens if we take an up, spin up, spin up, spin up? So now we've got an up. Perfectly all right, because each of them will have different colours. What is the total spin? Total charge, plus 2/3, plus 2/3, plus 2/3, gives me an overall charge of +2. Total spin, half plus a half plus a half, is 3/2. And that is actually called the delta double plus. You'll notice that the pluses indicate the charge of the particles. Let's design another particle. This one we'll call the up with spin up, down with spin down, down with spin down. We now know that the charge on this will be plus 2/3 minus 1/3 minus 1/3. That's 0. The spin is plus a half minus a half minus a half, which is minus a half, or a half. And that, of course, is recognisably the neutron. An up and a down and a down. And remember, these two are the only essentially stable combinations of quarks. All the others decay very, very quickly. So what about if we take an up, down, down, which is what we had for the neutron, but this time we have all the spins spinning down. Well, once again, the total charge will be plus 2/3 minus 1/3 minus 1/3, which is 0. But the spin will be minus a half, minus a half, minus a half. Well, that's a 3/2, plus or minus 3/2 spin. That is not a neutron. That is actually called a delta zero. 0 because it has no charge. But we're not just restricted to up and down. As we know, we've got a combination of up, down, or charm and strange, or top and bottom. So let's create some more exotic particles. For example, we could have an up, a down, and a strange particle. Those were, in the early days, those were the only 3 quarks that were discovered. Obviously, up and down came first, and then strange came later. That's why it was called strange, because it didn't behave like the others. Strange quark. And now if we look at that, we will find that the overall charge here will be 0, because a strange quark has the same charge as a down quark, so that's plus 2/3 minus 1/3 minus 1/3 gives you an overall charge of 0. And then depending on how the spins are aligned, you will either get plus a half, plus or minus a half, or plus or minus 3/2. And those particles are called epsilon particles, epsilon 0 because the charge is 0, or lambda 0, depending on how the spins are aligned. We could think of a particle where all particles, all the quarks were down quarks, with, let's say, all the spins spinning down. The charge on this would be -1 because it's minus 1/3 minus 1/3 minus 1/3. And the spin, of course, is going to be 3/2 because they're all spinning in the same direction. So it's a half plus a half, minus a half, minus a half, minus a half. It's minus 3/2. And that, again, that's going to be a delta minus. A minus because it's got a charge of -1. Or you could even have 3 strange quarks all spin down. Once again, strange has the same charge as a down, so it's minus a third, minus a third, minus a third, gives you -1. The total spin is going to be 3 halves or -3 halves, and that is actually called an omega minus. And you can keep on just combining different categories of flavours of quarks to make different designer particles. Now, in the 1940s, 50s and 60s, mainly I think 50s and 60s, before quarks were known about, protons and neutrons had been discovered. But as people found more and more high energy accelerators, or if they designed more and more high energy accelerators, they started to discover these other particles without knowing what the substructure of them was. So there was a great deal of fascination in what was called the particle physics field, that there were all these particles being discovered, and nobody quite knew why nature had so many particles, the vast majority of which, of course, decayed almost immediately, leaving just 2 basic particles that stayed for any length of time. And it was only when a man by the name of Murray Gell-Mann thought about it, he decided that basically these particles were not fundamental particles, as had originally been thought, but actually had a substructure. And he was the one who came up with the idea that there were 3 subparticles, which he called quarks. Sometimes he asserts that he meant them to be called quarks. Quarks, you take your choice. But once he had identified that there were things called quarks, then the reasoning for all these different particles became clear. They were simply just the permutations of those quarks and associated spins. Well, those are just some of the 3 quark or baryon combinations of flavours of quarks and spin that give us all the different particles that can be discovered. To discover them, of course, you need to have some kind of particle accelerator that will produce those particles fleetingly before they decay. But let's now look at the meson pairs that you can create. I said that you could create a meson that would always be a quark-antiquark combination, so we can sort of pretty easily draw the diagram. And if we're going to have a quark-antiquark combination, the possible quarks, of course, are up, down, charm, strange, top and bottom. And the antiquarks are, of course, anti-up, anti-down, anti-charm, anti-strange, anti-top and anti-bottom. And you can perm any one of these with any one of these to give you 36 combinations of quark-antiquark pairs. So I've drawn out a table that does precisely that. If we look at the top left-hand corner, you've got the up, anti-up meson, which is just a pion. The up, anti-down is the pi plus. The down, anti-up is the pi minus. In the early days, these were the pions that were well known. And then somebody found the strange quark, and that's what gave rise to the kaons. The Ks, you'll notice, all have strange particles. They are either the strange anti-up or anti-down pairs, or they are the up-down anti-strange pairs. But when you only had ups, down and strange on the agenda, then you had the pions and the kaons. But then a new particle was discovered, I've ringed it here, by 2 different groups. One called it the J, one called it the psi, and so for a while it became known as the J-psi particle. It was the first particle that was found that included a new quark called a charm quark. And that's essentially how the charm quark was discovered, through this new particle, this new meson. All I can show you at the moment is the up, down, charm and strange, but of course if I push up the table you can see that there are also combinations of top and bottom quarks with each of the antiquarks. So you've got 36 combinations of quark-antiquark pairs that make up the mesons. I think the very last one to be found was the bottom quark, which is called the upsilon, and that was found in 1977. All of the particles that I've talked about so far, whether they are the baryons, that's the three quark combinations, or the mesons, which are the 2 quark combinations, are those which are in what's called the ground state. When I talk about ground state, I basically mean that the particles have spin, but they do not have angular momentum. If you think back to the earlier video that I did in this series, I said that there were 2 types of spin stroke angular momentum. There is basic spin, which is where a particle essentially spins on its own axis. And there's angular momentum, which is where a particle actually orbits something else. Now, in a ground state, these particles that I have been showing you so far simply have spin. But if you energize them, then the quarks themselves can start orbiting one another. They have higher energy. And then you get angular momentum as well, and that changes the nature of the particles. But in their ground state, which is all I'm worrying about at the moment, you've got a particle which has spin. Now, quarks that we've been talking about are part of fundamental particles which together comprise what's called the Standard Model. And I've done a video on the Standard Model. I advised you to look at it earlier in this particular series, but the Standard Model can usually be described in a diagram form with a grid of a 4x4 grid, and the top 6 boxes are the fermion quarks. There's the up and the down, the charm and the strange, the top and the bottom. We've already referred to those. Those are quarks. They are also called fermions. The bottom 6 are for the so-called leptons. That's the electron, the heavier electron, which is the muon, and the even heavier electron, which is the tau. And their associated neutrinos, which is the electron neutrino, the mu neutrino, and the tau neutrino. And of course, all these particles have antiparticles. So you can have an anti-up, anti-charm, anti-top, and so on. They all have antimatter equivalents. The right-hand column is reserved for what's called the bosons, the gauge bosons, the exchange particles, the force carriers. We dealt with those, for example, in the last video. The photon, which is the force carrier for the electromagnetic force. The gluon, which is the force carrier for the strong nuclear force. The W plus and minus and the Z, which together are the force carriers for the weak nuclear force. You'll notice we don't have the graviton on this model, partly because no one has yet found a graviton, and we don't even know that it exists, and partly, of course, because gravity is not included in the Standard Model, which this diagram purports to show. Only 3 forces are included in the Standard Model. The 4th, which is gravity, is not yet included, and that is, I suppose, the next big challenge, to get a unified model that encompasses everything. These days we now have to add another box. People put it in different places, I'm going to put it here, and that is the Higgs, the recently discovered Higgs boson, which accounts for mass. So the Standard Model says that there are 6 basic quarks, 6 basic electrons, 4 basic gauge bosons, and then finally a Higgs boson, which has a slightly different function. And those are the irreducible minimum basic particles. So far as we know, these particles are not made up of anything else, and they are the basic particles of nature. And as far as we know, there aren't any others. Though there are some theories that say there might be more than one Higgs boson. There might be heavier Higgs. But that's to be discovered. It's rather strange because, in fact, nature only really makes use of, in terms of the fermions, the ones in the left-hand column. So why nature decided we needed heavier versions of them, nobody knows, because those heavier versions don't stick around for very long. they quickly decay into the lighter versions. Now that 4x4 array of quarks, leptons and bosons can also be represented mathematically. And that is the mathematical formula for the Standard Model. It's simplified, I have to say, and we're not going to go through it because we don't need to, save to say that what it purports to show is the way in which all those particles in the Standard Model interact with one another. And the Higgs field is included in the third and fourth lines. But basically, if you want a mathematical description of how things interact, then you need that particular formula. That formula, as I've said, does not incorporate gravity, because at the moment there's no way to incorporate gravity into it. Gravity is accounted for by Einstein's general theory of relativity, on which I have done a separate video. It's called the Einstein field equations, and those are, although they only look like one, they are in fact many, Einstein field equations which explain gravity. And the problem is that that formula and the Standard Model formula do not coincide. So the big prize now is for someone who can take that formula and integrate that one into it to form a unified model. One of the ways in which unification could be achieved is by a process called SUSY, or that's short for supersymmetry. The idea is that for all the fermions, that's the box, the 3x4 box here, these are all fermions, that is particles. All these particles, according to supersymmetry theory, have got a corresponding boson. And all these bosons on the right-hand side have got a corresponding particle called, a corresponding fermion particle. And the way that you change one to the other is that if you want to change a fermion to a boson, you just put an S in front of it. So a quark becomes a squark, an electron becomes a selectron, and a squark and a selectron are bosons. And if you want the supersymmetric equivalent of the boson, you simply put the word eno at the end, so you get a photino fermion, a gluino fermion, a vino or a wino but never a wino fermion, a xeno and a Higgsino. So this is the idea that for symmetry all the fermions have got boson equivalents and all the bosons have got fermion particle equivalents. Why will that help? We'll discover that in just a few moments. But here is the problem. None of those supersymmetric particles have ever been found. And if they had the same mass as their original particles, they would have been found. In other words, if there is a fermion called a photino, which is massless, like the photon, it would easily have been discovered. If there is a squark, which is a boson having the same mass as an up quark, it would easily have been found with the experiments that we have done. So the suggestion is that maybe these particles, these supersymmetric particles, have not been found because they are more massive than the particles in what we understand to be the Standard Model. Now, the most massive particle we have so far found is the top quark, which is approximately 175 GeV. The Higgs, which was recently found, is 125 GeV, and we needed the Large Hadron Collider to find that. So if we've got supersymmetric particles which are greater than 200 GeV, which would make them very massive, then small wonder they haven't been discovered yet, because we're only just getting into that kind of a range. So it may be that the Large Hadron Collider, once it has been upgraded and it has higher energy, will start to discover some of these supersymmetric particles if they are of the order of 200 GeV. Of course, if they are much more massive than that, then maybe even the Large Hadron Collider won't find them, and then we shall be stuck. either to abandon supersymmetry on the basis that we've never found any evidence of it, or just to cling to the hope that maybe one day we shall find the particles when we get a much higher energy a piece of apparatus than the Large Hadron Collider. But of course no such piece of apparatus is even on the cards at the moment, so you'd have to wait a very long time. So why do people cling on to this idea of supersymmetry? Well, basically because it could hold the key to three things. The first is known as the hierarchy problem, and this is about what's called the Planck mass. Now, I've done a video on this, it's called Planck units, and for the mass version you need to look at the third in the series of 3 on the Planck units. But basically there's a thing called a Planck mass. The way it works is this, that nature seems to have 3 fundamental constants. One is g, that's Newton's gravitation constant. One is h, or h bar, that is Planck's constant. And one is c, which is the speed of light. Those are fundamental constants of nature. They do not seem to vary. And you can combine those constants in order to produce the basic units of mass, length and time. And when you do that, you get what's called the Planck mass, the Planck length and the Planck time. And the argument is that if these 3 are constants of nature, you might expect nature to, as it were, focus on or build things around those Planck masses, lengths and times. Now, what is the Planck mass and how do you find it? Well, what you say is that you want some combination of G, H and C that will give you a dimension of mass. So you take G and H bar and C and you multiply them, or you, as it were, increase them by the power of P, Q and R respectively in order to find out what mass is going to be. So mass, which is obviously going to be to the power 1, is going to be G. Well, G has units of length cubed divided by T squared m. And so if it's raised to the power p, each of these has to be raised to the power p. H bar has units of length squared times mass divided by t. And obviously if that is raised to the power q, each of these has to be raised to the power q. C has, of course, is just speed, which is distance over time. So that's length over time, but since we're raising it to the power r, we raise it to the power r here. I'm going quite quickly here because if you need to check this, you'll find it explained in the videos on Planck units. And if you then, what you basically have to do is all of these lengths must cancel out because you've only got mass on this side, and all of the times must cancel out because you've only got mass on this side, and all of the m terms must cancel out to a single mass raised to the power of 1. So if you do that, what you find is that m becomes equal to the square root of h bar c over g. And if you do that dimensionally, if you look at the dimensions of h bar c and g, and you divide or multiply and divide the dimensions in this way and take the square root, you will get a unit of mass. And if you actually put in the actual values here, that's 6 times 10 to the minus 34 times 3 times 10 to the 8 divided by 6 times 10 to the minus 11 and take the square root, you will find that you will get 2.2 times 10 to the minus 8 kilograms. So the Planck mass, the mass that you get if you use the 3 basic fundamental constants of nature, is 2.2 times 10 to the minus 8 kilograms. Energy is mc squared, so if you want the energy associated with this mass, you have to take 2.2 times 10 to the minus 8 and multiply that by the speed of light squared, E equals mc squared, so that's 3 times 10 to the 8th all squared. and that comes to 3 times 10 to the 28 electron volts. Or if you like, 3 times 10 to the 19 GeV, since a GeV is 10 to the power 9. So that's 3 times 10 to the 19 GeV is the Planck mass. And yet the heaviest particle we have discovered is the top quark, which is 175 GeV. That's the top quark. So the question goes, if the kind of natural unit of mass, according to these three fundamental particles, is something as massive as this, 3 times 10 to the 19 GeV, when in fact the particles we discover are hugely smaller than that, why is it that nature has not built particles around its own natural Planck mass? Why are they so much smaller? And that's what the hierarchy solution associated with supersymmetry says. What it says is that for some reason the supersymmetric particles have effectively cancelled out all these heavier masses and left only lighter masses, which means that the particles we've observed are small and probably the supersymmetric partners are not much bigger. So there's hope for thinking that the supersymmetric particles are findable, because although they are heavier, and indeed they are probably heavier, almost certainly heavier than the top quark, they are not so heavy that you'll never be able to find them, because supersymmetry, the mathematics of supersymmetry, cancels out the really massive particles and leaves you with potentially findable supersymmetric particles. So that's the hierarchy problem. The second is unification. Now, in the last video I drew a graph where I looked at the strength versus time, and you remember I plotted, this is time now, that there are four forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. I said these were not to scale, since strong nuclear force is 10 to the 38 times stronger than gravity. But this simply shows that at the moment those are four quite separate strength forces. And I said that the assertion was that at the time of the Big Bang they were all the same force, so that if you plotted them back you would find that actually they all had the same strength at the time of the Big Bang. And that's the kind of assertion that was in the last video. Now that is not quite right. What you normally do is to plot not strength against time, but strength against energy. So at the time of the Big Bang, there would be a massive energy. We calculated something of the order of 10 to the 15 GeV. Actually, I think we calculated 10 to the 17, but the usually assumed number is about 10 to the 15. And very low energy, this would be now. Low energy. So time, in a sense, on this scale goes that way. Energy goes in that direction. So when you had a very high energy at the time of the Big Bang, you've now got a very low energy here. Here are the, I'm only going to plot three here. This is strong nuclear, electromagnetic, and weak nuclear. We don't put gravity on because at the moment we're not sure that that is part of the standard model. The idea is that if you plot them back to the time of the Big Bang, that they should overlap. But, and I've drawn that quite deliberately like that, the problem is that if you draw them as we now understand how they vary with energy, you find that at the time of the Big Bang, they do not overlap. They miss one another. But if you include into the mathematics the supersymmetric idea, then surprise, surprise, when you draw these three back to the time of the Big Bang, they actually all, if I've drawn it properly, they all coincide at the time of the Big Bang. So supersymmetry looks as though it's a means of achieving a uniform, at least for three, a unified version of at least 3 of the 4 forces, and as I've said, the big thing now is to find a way to incorporate gravity into the standard model. The third area that supersymmetry might be able to help us with is dark matter. Now, I've done videos on dark matter and dark energy, and as I explained, if you think about ordinary matter, that's the stuff that we see that the universe is made of, we conclude that that actually is only 5% of the universe we observe. There is something called dark matter, which is about 20% or 25% of the universe, and there's something called dark energy, which is the remaining 70% of the universe. So this we kind of understand reasonably. These we don't understand at all. Dark matter is what we assert must be there because that is what makes galaxies rotate in the way that they do, as I've shown in my video on dark matter. Dark energy appears to be needed because the universe appears to be accelerating in its expansion. You would expect it to decelerate because of gravity, but dark energy, which appears to be a kind of anti-gravity, causes it to accelerate, and we don't know what that is. But one of the things that dark matter could be a supersymmetric particle. And we can show that in a Feynman diagram, because what we know about dark matter, and the reason it's called dark matter, is that it doesn't interact with radiation. It doesn't, for example, interact with light, so you can't see it. So if we were to draw a Feynman diagram, here is a photon of light, and here is a dark matter particle. What we are saying is that there is actually no interaction between the two. So the dark matter particle just carries on as a dark matter particle, and the photon just carries on as a photon, and there is no interaction between the two that you can discern. And that's a Feynman diagram that shows nothing happens. There is no exchange boson, there is no force between them, there is no interaction, nothing happens. And if this dark matter particle is a supersymmetric particle, then that could explain what dark matter is all about. So supersymmetry is still on the table, even though we've not found any particles which are supersymmetric particles, in order to help explain the hierarchy problem, why our particle mass is not much more massive than they actually are, in order to explain the unification, to get all the forces to be of the same strength at the time of the Big Bang, and possibly to help solve the problem of what is dark matter. It could yet turn out that supersymmetry is wrong, but then we would need something else to try and explain these issues.